Hi, this is a video to help you through the activity on redox and reducing sugars. In the last activity, we talked about hydrolysis and condensation reactions of monosaccharides and disaccharides. Those are reactions where water is eliminated to form a disaccharide or polysaccharide, or where water is used to cut bonds between polysaccharides or disaccharides to make monosaccharides. Today we are going to talk about a different type of reaction, a redox reaction, that sugars can undergo. But first, let's remember what we've already learned about redox reactions. You've seen this reaction before, and you've identified the things that were reduced and oxidized in this reaction. In the previous activity on redox, we learned how to determine whether something was reduced or oxidized in an inorganic reaction by following the charge of the reactant elements. We know that this is an inorganic reaction because it doesn't contain carbon and it does contain an ionic compound. This is the same thing we've done in a previous activity. So let's just review. Iron in the reactants is a pure element, and so its charge is 0. In the products, it is part of an ionic compound. Because iron is a transition metal, you can't read the charge of its ion off the periodic table, so you have to infer it from the formula. It is a +3 in the product. It became more positive over the course of the reaction, and so it fits into the category for oxidation or loss of electrons. The oxygen reactant started out as a 0 because it is a pure element, and in the ionic compound, it was a -2 charge. Just like oxygen will always be in an ionic compound. I could read this directly off the periodic table, or I could infer it from the formula. Here we can see that oxygen has gone from a 0 to a -2, so it's become more negative. It fits into this category where it is reducing or it has gained electrons. Whenever you're following inorganic reactions, you're going to use charge to determine which thing is oxidized and which thing is reduced. We also talked about another situation for organic compounds where you follow the gain or loss of hydrogen and oxygen. Here was the example that we saw before. Ethanol plus nicotinamide adenine dinucleotide goes to an aldehyde. In this case, it's acetaldehyde and NADH. Plus a hydrogen ion. In this case, the NAD plus is a representation, or it's a shortcut for representing the whole molecule. And here we see the same letters with a hydrogen, and this hydrogen literally means a hydrogen atom. In this reaction, NAD plus had no change in the bonds to oxygen, but we can see that it's gained a hydrogen. Therefore, it fits into the category for reduction. Ethanol, in this case, had no change in the total number of oxygens, but the carbon here only had 1 bond to oxygen, and the carbon here gets 2 bonds to oxygen. So it has actually gained bonds to oxygen. When you have a large molecule and there are lots of things happening, pay attention to what's happening specifically to the carbons to determine whether the molecule has been oxidized or reduced. In this case, the ethanol has gained bonds to oxygen to form acetaldehyde. We've also changed the number of hydrogens. In the reactants, there are 6 hydrogens, and in the product, there are only 4 hydrogens in this molecule. So it's lost hydrogens overall, but you could also say that this carbon has lost a bond to hydrogen, and so has the oxygen. Either way you look at it, gain of oxygens or loss of hydrogens, it tells you that ethanol has been oxidized. I'd like you to pause for a second and think about what are the reducing agents and oxidizing agents in this reaction. The oxidizing agent is something that oxidizes something. So the ethanol here was oxidized, and so wherever its electrons went must be the oxidizing agent. The thing that was reduced is the oxidizing agent. So NAD plus would be the oxidizing agent. The thing that was oxidized is the reducing agent. If it was oxidized, that means it gave its electrons to something else and it reduced that other thing. So this is a reducing agent if it was oxidized. I'd like to explain a little bit more why you can follow bonds to oxygen and hydrogen to determine what was oxidized and reduced. Here are three functional groups. In the middle, we have an aldehyde. And over here, we have a carboxylic acid. And over here, we have an alcohol. Let's start in the center. Look at this aldehyde. Notice that it has a double bond to oxygen and that this is a polar bond. Therefore, I can write a partial positive on the carbon and a partial negative on the oxygen. This is a polar bond. And the oxygen is more electronegative than carbon, and so it pulls electron density away from the carbon. Going from an aldehyde to a carboxylic acid, you add a bond between carbon and oxygen, or you add an atom of oxygen. What this does is increases the polarity of the carbon. You have 3 bonds between carbon and oxygen now. And now there are 2 oxygens that are pulling electron density away from carbon. So the carbon in a carboxylic acid is much more positive than the carbon in an aldehyde. And I'm trying to show this by the size of my partial charge symbol here compared to here. Therefore, this carbon has lost electrons by gaining a bond to oxygen. When I oxidize a carbon by adding bonds to oxygen, I'm really taking electron density away from the carbon because the oxygen pulls electron density away from the carbon through polar bonds. The opposite happens when I remove bonds to oxygen or when I add bonds to hydrogen. Both of those things are happening in going from an aldehyde to an alcohol. I have gone from 2 bonds to oxygen to only 1, and the carbon here has gained a bond to hydrogen. This carbon has a very polar double bond. It's essentially equal to 2 separate bonds between carbon and oxygen. And over here, I have only 1 bond between carbon and oxygen. This oxygen is pulling electron density away from carbon, but not as strongly as it does in this case over here. In addition, the carbon has replaced its oxygen bond with a new bond to a hydrogen. This is a better sharing of electrons, and the hydrogen releases some of its electrons to carbon. Now this carbon is not as partially positive as this carbon is. So in removing a bond to oxygen and adding bonds to hydrogen, this carbon is less polar or less charged, and in this case, I'm reducing because the carbon is gaining more electron density. So in adding bonds to hydrogen or removing bonds to oxygen, carbon is gaining more electron density and it's becoming reduced. In sugars, the aldehyde functional group is very electron poor. This is a very polar bond, and this carbon is reactive. This is the anomeric carbon. The anomeric carbon of any sugar is very reactive. One of the reactions that it will undergo is an oxidation reaction. When you oxidize an aldehyde in an aldose, you get a carboxylic acid. You've gained a bond to oxygen, and this carbon is more partially positive than it was in the reactants. These reactions are not always balanced, and that's okay. Notice that this reaction is not balanced as written because I have 1 more oxygen in the products than I have in the reactants. You can balance it though, and if I wanted to balance, I would add a molecule of oxygen plus 2 of these molecules to give me 2 of the new molecules with 1 more oxygen each. Sugars will also go through reduction reactions. In a reduction reaction, the anomeric carbon is the most reactive part again, and in this case, you go from an aldehyde to an alcohol. When you add hydrogens and remove oxygen bonds, you have to add the hydrogens 2 at a time. When I break this bond, there will be 1 electron in each atom that needs to have a new bond. And that new bond is made to hydrogen in both cases. So whenever you add hydrogen to reduce something, you always add 2 different hydrogens, 1 to each side of where the double bond used to be. This is a reduction reaction. Notice that as written, it is not balanced. That's okay, you can balance it, but know that they will sometimes be written not balanced. Here's the balance. I would simply add a hydrogen molecule to the reactant side, and now it's just automatically balanced. I've just shown these reactions for an aldose. But please know that ketosis can undergo these reactions as well, because in the presence of oxidizing or reducing agents, the ketose, like fructose, can rearrange into its structural isomer, an aldose. So this rearrangement happens very quickly in solution in the presence of oxidizing and reducing agents. So fructose and glucose, all aldoses and ketoses, can undergo the types of reactions that I just showed on the previous slide. Oxidation is a very common reaction that you'll do in the clinic to determine whether a patient has diabetes. One of the most common tests is called the Redox test. The reaction representing the Redox test is in front of you. Here's an example where we take D-glucose added to copper ions, and in this case it's copper 2, and we get gluconic acid and a new ionic compound. I'd like you to notice that there are carbon compounds in this reaction, from D-glucose to D-gluconic acid. These two are organic molecules. And so when I am trying to determine whether D-glucose has been oxidized or reduced, I will follow the bonds between carbon and oxygen and carbon and hydrogen. There's also an ionic compound in this reaction. And so this is actually a mixed reaction. It has both organic and inorganic components. When I want to determine whether copper has been oxidized or reduced, I need to follow charge. In this case, you're going to apply both sets of rules for determining oxidation or reduction. And you have to apply the organic rules to D-glucose and the inorganic rules to copper 2. D-glucose to D-gluconic acid, there is a gain of an oxygen atom and a gain in the bonds between oxygen and carbon. Therefore, D-glucose has been oxidized. In copper, this copper is going from a 2+ ion to a 1+ ion. You'd have to infer the charge on the copper from this formula. So we're going from 2+ to 1+, and that means we are becoming more negative. It's the opposite of becoming more positive. And so the copper here is actually reduced from copper 2 to copper 1. The copper has gained an electron. Please notice that if you use the wrong rules in the second case, you would actually think that copper was oxidized because it has gained oxygens. It's very important to apply the right rule in the right situation because otherwise you could deceive yourself. Glucose here is oxidized and it is the reducing agent, so D-glucose is the reducing agent. It's called the reducing sugar. Copper is the oxidizing agent because it is reduced. Now, D-glucose being a reducing sugar is useful. You can use this reaction to determine if there are reducing sugars in a solution. Here is a test tube that has a copper 2+ solution in it. Copper 2 is a blue color. If you add sugar to this test tube, you know that sugar water is colorless. But if you add sugar to this test tube, you would end up getting a red precipitate. The red is from the copper 1 oxide. This is a common test that's used in clinics to determine whether someone has a lot of free sugars or reducing sugars in their urine. If they do have a lot of reducing sugars in their urine, this test will tell you. And the meaning of this test is normally that the patient has symptoms of diabetes. You'll often see tests like this on a stick, which can be immersed in urine. And the color on the stick will tell you something about the amount of free sugars or reducing sugars in the person's urine. If there are a lot of reducing sugars, it means that the person could be diabetic. What does it mean to be a reducing sugar? Well, a reducing sugar is anything that has an anomeric carbon that can react in an oxidation reaction. When an anomeric carbon is part of a glycosidic bond, it's protected from this reaction, so it won't happen. But if the anomeric carbon is not part of a glycosidic bond, it is said to be free, and it can react, or it can act as a reducing sugar. On your activity, you have a number of mono and disaccharides in front of you. The first thing I'd like to do is recognize which carbons are the anomeric carbons. Please pause the video now and circle the anomeric carbons on these molecules. The anomeric carbon is the carbon that has 2 bonds to oxygen. It's usually written at the right-hand side of the molecule, but not always. We can find the anomeric carbon easily by first finding the oxygen in the chain. The anomeric carbon is always attached to this oxygen, so it could either be this one or this one. In this case, it's this carbon because it has 2 bonds to oxygen. Now I've circled all of the anomeric carbons. Notice that in each monosaccharide, there's 1 anomeric carbon, and in each disaccharide, there's 1 anomeric carbon per ring. Now I'd like to recognize which of these are not free anomeric carbons. If something is not free, that means that it's part of a glycosidic linkage. On this slide, I've circled those ones in blue. These are the anomeric carbons that are not free. It means that they will not act as reducing sugars. They will not react in an oxidation reaction, and they will not give you a positive result for a Benedict's test. On the other hand, the anomeric carbons that are free are in pink. These are free anomeric carbons. If a molecule has a free anomeric carbon, it will act as a reducing sugar. It can react with copper and produce a positive result for a Benedict's test. Even in the case of D-lactose, where there's 1 anomeric carbon that's not free, by virtue of the 1 anomeric carbon that is free, this is classified as a reducing sugar. In monosaccharides, disaccharides, or maybe even tri- and tetrasaccharides, basically where there are only a few sugar units linked together, when there is 1 free end or 1 anomeric carbon that's free, the sugar will be classified as a reducing sugar. In the case of a polysaccharide, this is different. Let's define some terms. This is a cartoon from your textbook. This is representing the 6-membered ring with an oxygen that's common to many sugars. A monosaccharide is 1 of these units, a disaccharide is 2 of these units, and an oligosaccharide is something that has from 3 up to 9 units. A polysaccharide has many, many units, up to 10,000, and these are very common in our bodies. For monosaccharides and disaccharides, and some of the shorter polysaccharides, if there is a free anomeric carbon, they will be reducing sugars. But when it's a polysaccharide and there's a free anomeric carbon, it's not considered a reducing sugar because there will be only 1 free anomeric carbon for 10,000 sugars. Here are some more cartoons from your textbook. And in these cases, the little hexagons are representing the sugar monomers, and they're showing the ends with blue. This is a non-reducing end, and like the anomeric carbon would be here, here, here. And then you have 1 reducing end. When you have a very long chain of sugars with only 1 reducing end, the sugar overall is not reducing. Basically, it decreases the number of sugars that have free anomeric carbons by linking them all up, and it ends up giving you a very low concentration of reducing ends. So when you have a lot of these polysaccharides in your blood or in your urine, it doesn't give a positive result for the Benedict's test because there are very few of these reducing ends. Here's another example with a branched sugar. Notice that in this case there are many ends, but most of them are non-reducing. And for any of these branched sugars, there's only 1 reducing end. In these images, there are a limited number of sugars that are shown here. But in real polysaccharides, remember there could be up to 10,000 units, and only 1 of the ends is a reducing end. So it's not enough to cause a positive result for the Benedict's test. Polysaccharides like starch and cellulose are non-reducing sugars. Despite the fact that they have 1 reducing end, they are called non-reducing sugars because they cause a negative result for a Benedict's test. This is the end of the video. Please make sure you can complete the questions in the check for understanding and check your work against the key. Don't forget to do the problems in your textbook and especially at the end of the chapter for extra practice. Thanks for watching this video on redox and reducing sugars. If you have any questions, please post them in the comments. And if you found this video helpful, please vote and let me know.